Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jumana Tariq Nabil Abdurazik. I'm studying for a master's degree in petroleum engineering at University of Houston, and I will be your moderator this afternoon. Today, we're pleased to welcome Dr. Mohamed Ghareeb, a very special guest from Egypt. Dr. Mohamed Ghareeb has a PhD in petroleum engineering, specifically in artificial lift, production engineering, and operations. Dr. Ghareeb is a technical and business professional with over 34 years of experience in oil and gas business operations, management, engineering, sales, and teaching. Dr. Ghareeb was the Eastern Hemisphere Technical Director at Lufkin, as well as the Regional Technical Director of the Middle East, North Africa, and Turkey at General Electric Oil and Gas. He then worked as Vice President of the Eastern Hemisphere at SSI Lift. Now he works as the Strategic Business Director for the Eastern Hemisphere at Weatherford and Petroleum Engineering Professor at Future University in Egypt. And today he will continue to share with us his expert opinion on the artificial lift techniques. If you haven't already, please make sure to check out our previous sessions on Petro YouTube channel and join our Facebook page, Arab Oil and Gas Academy, for the latest updates on our September and October courses. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask you to give your full attention to Dr. Mohamed Ghareeb and help me in welcoming him. Please welcome one of my all-time favorite professors, Dr. Mohamed Ghareeb. Hi, Dr. Ghareeb. Thanks for joining us today to pick up where we left off in the Artificial Lift Technologies course.
Thank you, Jumana. Thanks. Assalamu alaikum. Good morning, good afternoon, good evening, and welcome back, all of you again, for our third lecture today. I'll try just to not be too long, I'll try just to finish within 1.5 hours, a little bit more could be. However, we are talked before about different type of artificial lift, different geometry. I just remind you about 1 slide or 2 slides about what already talked before about. And we said that we have a variety of artificial lift system. Some of them can be a mechanical assist, some of them can be gas or formation assist, just to lift fluid from the oil, to lift my desired production. The production, what I want from the oil to the surface with a required wellhead pressure. Then again, the artificial lift is required to reduce the bottom hole flow pressure against the reservoir to allow the reservoir to produce the desired production, the design production based on well productivity. Meanwhile, it's required to creating, if it is pumping system, creating bottom hole flow pressure again, just to overcome, just to increase the discharge pressure, which will allow the fluids to reach to the surface with the desired or the required wellhead pressure required to move this fluid to the separators. And we already started with road lift system, and we said we start with road lift system because it is the most popular artificial lift system worldwide. More than 70 to 74% of the number of well producing by road lift system. For that reason, we started with this. And the second artificial lift we'll talk about is the electric submersible. For the beam pumping system, we talked about the system itself, the component of the system, and the design of the system, how to design. We give some hint about the design, what type of software we need to design, and what we need to consider while we design the beam pumping system. And we said there is 4 main components for the reciprocating or beam pumping system. The 4 main components is starting from downhole pumps, and then rod string, and after that, at the surface we have another 2 main components, two main components downhole, and 2 main components at the surface, and plus the prime movers. The pumping unit the prime mover is rotating, and it's just provides the rotary motion to the pumping units, which is transfer this rotary motion to reciprocating up and down. This reciprocating up and down motions is transferred through the mechanical link. It is a sucker rod string to the downhole pump, which is working in the reciprocating motion up and down, and we said the downhole pumps is just a mechanical pump with two main valves, two non-return valve, non-check valve. Again, it's open by delta B, closed by change of the direction of flow. If you understand this is a very basic concept, you can understand how to design, how to select the best pump for you. Then the reciprocating sucker rod pumping system or rod lift system is a chain of four main components, 1, 2, 3, 4. Downhole pumps, sucker rod string, pumping units, and prime movers. If one of these chain not work, the rest is not work. If one of this chain is just perform as a performance law, it would affect for all the rest of the system. Then again, the beam pumping system have four main components. All these four main components: prime movers, pumping units, rod string, downhole pumps, plus some other accessories. We have a lot of accessories. However, today we'll start to go about analysis, how to analyzing your wells, how to know your wells is running good or bad, what's the problem affecting on the system performance and system capability, not only performance, capability. When I design the system, I need to consider all that. For example, if I have a gas, what I need to consider. What I need to consider for downhole, what I need to consider for the surface equipment, what I need to consider when I design, selecting all these together, if I have a sand, and so on. While my system is running, I should be not blind. I should be understand how it's running. It's running in its good performance. It's running in high performance, low performance. Some of the parts of the pumping units is performing well or just performing poor and so on. Then today I will start with analyzing the sucker rod pumped well. In very brief symbols, in very brief slides, I will try just to show you what is the main important, because analyzing the system, it's a big subject, not only for sucker rod, for all type of artificial lift, not only for artificial lift, for all machine, for your life, and so on. Then how to analyze your system, how to get the maximum performance, how to get the maximum output out of your system. In order to do that, you need to understand what I need to know, how to analyze things, what factors affecting in my system, what factor affecting in surface or in downhole, how to solve this if there is a problem, and so on. Then analyzing the sucker rod pumped wells or just reciprocating pumping wells, beam pumping wells. I try to give you four names in order to be familiar with all names. If you notice, I changed it, but at the end, it's the reciprocating sucker rod pumping system. Analyzing the sucker rod lift and pumping system, usually it's starting from your well inflow performance. Either when design, I show you before, when you design the system, you need to start with your well inflow, the current well inflow and predicted well inflow, because maybe you have a reservoir with some declining in pressure, some change in flow properties, whatever. I need just, if I want to analyzing and design the system, I need to know what is my well inflow performance, current condition, and I recommend also for you predicting what will happen after 6 months. This current condition will be the same or just change after a few months in what I expected failure to have, what I expected performance, what I expected production. Not only that, remember the total system efficiency? And I show you an example about total system efficiency for my system. I need to identify well that can have some improvement in downhole and improvement in the system itself. Remember, rod lift system, since you put, not rod lift only, all artificial lift, since I put the artificial lift system in operation production, then each barrels, each one movement of my system, I pay against that. Then I need to have the highest possible system efficiency, which analyzing surface and downhole, which can be allow me to analyze each part of my system. Pumping units, if I found my total system efficiency start to go down, dropped, and my downhole pumps start to analyze each system. My downhole pumps working very fine, rod string working very fine. Then the problem in the surface equipment. I start to measure input and output of the surface equipment. Maybe have some bearing on the pumping unit have problem. Maybe the rod string downhole and so on, I need also one of the main important subject to analyze always my subsurface rod pump, how it's working, how it's running. Still the valve, remember, this pump is a mechanical, pure mechanical pumps. All valves, steel or just type of alloy steel, stainless steel, whatever type of downhole equipment is a mechanical. With the time, can we have tear and wear for all that mechanical part, mechanical equipment? I need just to know if the pump is running okay or not. With the time, maybe the bottom hole condition change, fluid properties change, gas increase, decreased water as a gas liquid ratio, what happened? What happened for sours condition and so on. Also, if there is any downhole gas separators, I need to analyze them from time to time. It's performing well or just performing poor. It's separated what the design for it got the gas or not. Also, mechanical loading, the loading on the road, the loading in the pumping units, the loading in all my system. Is the mechanical load is going well or the mechanical load increased? Mechanical load increased, for sure there is some problem or something change. Maybe it's not problem. Some condition change in the wells. Water cut increased, then my loading increased. Gas increased, then my loading decreased, and so on. Then at the end, I need to analyze my prime mover, the source of the power, source just providing the motion to the motor. This not only this just highlight the main important part, but however, you need to analyze every single point in your system. Whatever you do, it's your gain. This is just how to do that, how to analyzing the system, what tool I need to analyzing the system, and how to perform that. For well and flow performance, I need to know the well test. I need to just measure the flow rate and bottom hole flow pressures, static reservoir pressures, and so on. I need to know that. I need to analyzing this flow. But for the other, what tools I need? Then for each type of artificial lift, there is a certain monitoring tools called monitoring and optimization tools. Monitoring, just to monitoring the system running, system equipment, how it's running, how it's performing. And optimization from that monitoring and measurement of the parameters, what I have, how can I increase the performance? How can I have the best possible, the optimum conditions, of my system and so on, Then what information I need? I need to know my well pore description for sure. I cannot analyzing the wells and have a blind. What is my well pore condition? What is my completion? Maybe I use special completion. I have some special condition. I use special condition. Remember, for the completion for rod lift system, I inform you there's different type completion. There is a simple completion for single zone or for more than one zone, but producing combined, or just for selective completion and so on. System design. What is the original design and what is the current design? What is changed in the design? Do I take some, just what we call some precaution while I do design? Do I do a lot of assumption while I run my initial design because there is no enough data, and then now I have more data, then I need to rerun my design again according to the new data, because based on the new data, for sure you need to run the design to understand how is your system running, how it's working, and so on, All your recent representative well test should be have in your hand. My recent well test is give you how much your productivity is a problem from reservoir or from the system. Maybe you found your system start to face some low total efficiency. But low total efficiency is not mechanicals. Can be reservoir start to be depleted. Maybe I have my production start to go down. Maybe I found my volumetric efficiency start to go down. Then I need my well test. I cannot do any analysis or design without data. Whatever data you have, as much data you have in your hand in front, you will have a best design also. For rod lift systems, there's two main important tools just can be measured my system performance and give me indication how the system is running. It's one of them is called Dynamometer card. Each one working with a rod lift system, reciprocating rod lift system, he will know this name, dynamometer card, dynamometer analysis. Not only that, from dynamometer card and dynamometer analysis itself alone, maybe it's not enough, but dynamometer card with a measurements of producing bottom hole and static bottom hole pressure. What is my bottom hole pressure as a production or as a static, is there is a tool? Yes. From dynamometer, some people can have a very good estimation with a very high accuracy about bottom hole pressure. But meanwhile, there is a tools usually used not only for rod lift, for some other rod lift system. It can give me measures the flow level and the bottom hole, calculated the bottom hole flow pressure also. What my current production equipment setup, how the setup of surface and downhole equipment, my current production and running. What is the energy efficiency? The energy, it's the power source to my system. It's stable energy or fluctuated, have some problem which can be affecting my motor and my system and so on. Fluid properties with the time change and past history. What's the past history for that system and so on. All this data you must have at a minimum data in front of you. But if you have more data than this, will be excellent and well to have that to analyzing your well and so on. What is a dynamometer? How to analyzing the well? One of the very important tools for rod lift system. No one worldwide have rod lift system and doesn't know what is dynamometer. No one worldwide have rod lift wells or rod lift system and it's not run dynamometer. There's different type of dynamometer. There is what we call, it's just movable dynamometer. You can go and run dynamometer like you have a camera and takes snapshot about your face and your photo or whatever you have, and then you can analyze. Or you can have like a videotapes dynamometer continuous, just sit up at the wells, which is measure continuous dynamometer, which is called well controllers and so on. However, the principle is the same. It have the same principles as the dynamometer. Then the dynamometer is the most valuable tools in analyzing the performance of reciprocating sucker rod pumping system. And as I mentioned, there is two configuration or two setup of that dynamometer. Either dynamometer like this one, it's a movable, portable. You can have this one in your truck with your car, your truck. You go to the website, make your all installations. You are connecting, measuring, see how it's going on, and then after you finish, dismantle all these equipment, tools, cables, and you can go to run to the other well. Or according to all the current technology and the majority of the bigger producer and the company, it's used what we call, at each one there is a dynamometers. There's what we call the well controller, well managers, which continuously measured all the load and analyzing it, the load. Not only that, it's also majority of the company, especially the big company, connecting this to SCADA system, to internet. While you are sitting in your office, you can see how the well is running, how the downhole pumps is performing, how your surface equipment you're performing. Some people is installing even camera, which can see the wells, and so how it's running, how it's going on, how it's performing, if there is a leak, if there is no leak, downhole pumps, you can do analysis. Some other people based on that, and if you have some smart, just well managers or just prime mover with what we call like a variable speed drive or hydraulic pumping units, you can change the parameter from your office, not only from your office, even from your mobile, using your mobile, from your mobile app. You can know the performance of your room, how it's running, how it's going on, or how much production even, with some good accuracy, some setup you can have. What is a dynamometer and what looks like? Do we have one type of dynamometer, different type of dynamometer? How the dynamometer can inform me about the problem and the type of, for example, if I have downhole pumps, one of the valves have problem, leaking. Is a dynamometer capable to tell me, yes, you have traveling valve, have problem. Yes, you have standing valve, have problem. No, the problem came from your pump barrels. No, this problem, not from the pump, you have a problem with the tubing. No, all your problem came from pumping units and so on. So let me just talk you about, in very brief, just remember, all this is course just to put all the basics for you, and then you can go for any advanced course and so on. What is a dynamometer? And how it looks like? And where is I measure the dynamometer? And how I can measure the dynamometer? Dynamometer, as I mentioned, is a diagnostic device used in reciprocating sucker rod pumping units just to measure to measure the load at the top of the polished rod. This is a polished rod, and this is the top of the polished rod. If just you take, just increase zooming in this area, you show this area, this carrier bar, this clamp, this polished rod. This is what we call load cell. Load cell is installed here. Load cell it's sensitive the load of the rod, because there is a clamp and all the road below this one is sensed by this load cell. Then this load cell installed at the top of the load polished rod. And with a pump cycle going, just a complete cycle with a 360 degree, because going up and down, and the motor going for one revolution, one rotation. When the motor is complete one rotation here, the pumping units complete one cycle, up and down. Downhole pumps complete one cycle, up and down, one stroke. Then the dynamometer at the end, we can say it's the plot of the polished rod load, the load here at the polished rod. Okay, versus the position of the polished rod. The polished rod is here, or here, or here. Whatever the polished rod is moved, when the polished rod is moved, is measured the position. Where is the position of the polished rod? Then my dynamometer cards, what we call, this is surface dynamometer card. Remember, I will show you later on, there's two dynamometer cards. One is a surface dynamometer card, which is measures the surface, the load at the surface. Then the load at the surface is called surface dynamometer card when I measure that. But how, if I measure the load as a surface, can be predicted the downhole of my downhole pump, the load of the pump, because it will affect it. The surface dynamometer card, this card will affect it with the fluid, was affected with the road, with the friction, with the pumping unit, geometry of the pumping units, and so on. Then there is some technique should be used to avoid, to eliminate it, all that, and give me only the performance of the downhole card. Let me repeat it again. The surface dynamometer card, which is measured at the surface using load cell and position. Load cell, it's just fixed between clamp and carrier bar, and the position, which is measures the position of the carrier bar or the polished rod up and down within one complete cycle. This is what we call dynamometer card. Loads in this axis, position in this axis, and this shape called surface dynamometer card for one complete cycle, like 360 degrees cycle. The top part of this dynamometer card is represent the load in the upstroke, while the polished rod going up, then starting from a certain point up to the end point, going up and up. Going down, they have the down load in the down shape of this card. In complete cycle, closed loop like this, called surface dynamometer card. And the surface, remember please, surface dynamometer card is the measurement of the load at the surface. But my pump is running downholes, okay? And for the surface dynamometer card, or just simulated what? Simulated the load, at the surface. Just this is what you call surface dynamometer card. And for downhole condition, it's not an easy to just simulate only the downhole pump, with the surface dynamometer card. Because surface dynamometer card, it's affecting by flow load, affecting by rod string, how the rod string looks like, what it's a taper rod string, is not taper rod string, what's the bouncy effect, what's the gravity of the fluid, what's the viscosity of the fluids, how is it affecting on the rod string, how fast I running my system, as a speed, especially speed against stroke length. This is the two main function, because if I run, for example, 1 stroke per minute with a stroke length 100 inch going up and down 100 inch for 1 stroke per minute is completely different. If I run my system with 1 stroke per minute for a stroke length, for example, 200 inch, then the speed will be double if the stroke length was increased. Then all that harmonic what we call harmonic motion effect on the shape of the downhole surface card. For that reason, you found surface cards is not an easy interpretation of the card, and just analyzing of the card really is not an easy and not a lot of people can be understand this unless you have a certain experience in the field of road depth system with 5-6 years experience or more. Maybe you can understand, and even it's not an easy to understand downhole. But however, surface dynamometer card, it's the first point in dynamometers, and also effective with pumping unit geometry. Remember, I inform you that for the pumping unit, there is different geometry. Have class 1, class 2, class 1, class 3, like a conventional pumping units, enhanced geometry. It's like Mark II pumping units, air balance pumping units. Not only that, not only beam pumping unit, even vertical reciprocating pumping units is different. Then the shape of the pumping unit geometry balancing is a counterbalance. And so all that's effect on the shape of my surface dynamometer card. Mechanical friction of the road and tubing, viscosity, and so on. Then the surface card being affecting with so many parameters, so many factors. It's not an easy, just, to analyzing and not an easy to standardize even, because if you look to the factor effect on that, you found more than 100 factors. And so then how can I standardize all that surface dynamometer cards? In surface dynamometer cards, really, it's not an easy to analyze, but it's important. It's a starting point. It's important even to analyzing the surface equipment and so on. Then what happened downhole? How we can analyze it? One of the very important factor for me, also downhole, how's going on downhole and so on. Then the manufacturing and the engineering start to think about how can I analyzing or simulating or measured my downhole card. Then I have two cards. One what we call surface card, another card, one is called downhole card. Surface card is the measurement of the fluid loads at the surface, polished road load against the position. Then downhole card, let us just start this and we'll change the word again after, just a while. Let us to consider it is a load against position, but it is a fluid load at the pump simulated like you move your load cell. Remember the load cell which installed at surface? Remember that if you simulated your load cell this and you move to the top of the pump, you eliminated the weight of the road, the weight of the pumping unit geometry. And with this simulation, then the downhole card is measured the fluid load only. Fluid load against position. Surface card is measured the fluid load, measure the road loads, measure the acceleration loads, and a lot of load in the surface. How the downhole card, it's measured or just it's a measured or calculated. Majority just all downhole cards, because since it's not an easy to run a downhole load cell and run with a cable from downhole to the surface, and because since this unit it is a reciprocating unit up and down, then the mathematical engineer and say start to simulate it. Simulate, just say, okay, use my wave equation. The road's running here like a very small waves, what we call like wave. And one of the engineers called Sam Gibbs start to analyzing it and start to say, okay, let me simulate the performance of the road string like a wave equations, like a wave behaviors, and start to simulate like he moved this load cell to the top of the pump and start to eliminate it with this wave equations with a lot of factors, he eliminated the road of weight fluid, the friction, the pumping unit, and only have the weight of the fluid over the pump, which is can measured here for the downhole. Then the downhole card is a measurement of the fluid load at the top of the pump, or just not a measurement, it's just a calculated fluid load at the top of the pump against the position. And the people validated this by they are running downhole a load cell, and in the lab in some special wells start to evaluated how much accuracy and so on. Really found accuracy. It's very high accuracy, over 98, 95% accuracy, especially if there is no gas. Sometimes if there is gas, the accuracy can be a little bit affected, but majority now it's with a new technology, with an improvement in mathematics, and so they are able to calculate the downhole cart with a very high accuracy, reach to more than 98, 99% as accuracy. What is a downhole cart and how is running and how is measurement and what point in each downhole cart is running? Remember, I inform you that the downhole cart is the measurement of the fluid load against the position of the plungers inside the pump, how it's going on. This is a position. And this, if you remember, this is a downhole pumps. Upstroke, troubling valve, close down, standing valve open, downstroke, troubling valve open, standing valve close, going up like this, up and down. Then let us to see what each point here, in order to understand and to know how to analyzing the downhole cart, you need to understand the shape of the cart, how it's running, how it's going on, Let us start with the first point, while the standing valve and troubling valve need to close, the pump close in this position. If the pump closes this position at point A, this is starting of the upstroke. I start, in the upstroke, I start to go up like this. Starting the upstroke, the two valves close. Then when you start to go upstroke, troubling valve start to hold the load, but start to not move, because yes, it's as soon as the change position, then it start to hold the load. Then all the load start to be transferred from the standing valve, from the tubing to the top of the traveling valve, which is lifted by the rod string. Then the rod string stretches. This line can be vertical like this, can be a little bit, deviated like this, and so depend on your rod string and design. But however, in the ideal case, in the good case, and you will find this in a lot of wells in the same shape like this exactly, Then troubling valve, here is troubling valve, it's closed, standing valve is closed. As soon as going up like this, troubling valve is closed, but standing valve still here is the standing valve closed until we reach to point B, standing valve, because the rod already lifted all the fluids. Plunger left, plunger and the rod left all the fluid. At this point, okay, troubling valves start to move. Once troubling valves start to move, even 1 millimeter start to move, then creating a gap here. These are closed cylinders, and you have a fluid here. Then the pressure here start to be decreased. When the pressure here start to be decreased, and below the standing valve, it is a pump intake pressure, the formation pressure. It depends where is the pump you are sitting, Then the pressure below standing valve will be higher than the pressure above the standing valve. Then start to be open while traveling valve is closed now and move up, like, from here up to here, start to move up. While it's going in this area from B to C, traveling valve is closed, standing valve is open, and all the fluids above the traveling valve start to displace inside the pump. What happened in point C? Point C, if you look to point C here, point C, standing valve start to close. Why? Because when you start to change the direction of the fluid, then change direction of my plunger, the flow direction start to change. And if you remember, I tell you, for the pump valve, it changes the direction of the fluid. The standing valve is closed. And at this point, also traveling valves start to be here in this area. Standing valves start to be here still closed, But while start to going down in this area, still the condition is the same. Traveling valve at point D here, all standing valve is closed. Traveling valve start to be open because the pressure, he already compressed the pressure below it with a pressure higher than the hydrostatic head. This if the fluid below the standing valve is a single phase fluid, and if the pump completely filled with the fluid below the traveling valve. If there is a gas, we'll see the condition. The traveling valve will delay to open because of compressed. But assumed here, you have a complete pump fillage, and you have a single phase flowed liquid phase. Then when you start to go down, troubling valve start to compress the fluid below the pump. When you start to compress the fluid below the pump, the pressure below the troubling valve start to increase. When the pressure increases more than the hydrostatic head above the pump plus the wellhead pressure, and so is increased more than this pump discharge pressure, this will be open and transfer all the fluid loads here to the standing valve, and the cycle start to be repeated. Then the downhole pump, it's only downhole cart affected by the fluid, and the valves open or closed, affected only with the pump. Okay? The downhole pump, since it's the downhole carts and downhole pump cart, it's just surveyed like this and only give me the performance of the downhole pump. What can answer me? What information it can give to me while I am analyzing the downhole pumps? First of all, he can inform me that is the well is pumped off. What mean pump it off? Pump it off, that mean the pump start to be running with the capacity of the pump higher than the capacity of the formation. For example, if the formation only producing 100 barrel per day, and my pump going up and down with stroke length, stroke per minute, pump size to produce 200 barrel per day, but the formation produce only, for example, 100 barrel per day, then the pump, only 50% of the pump full with liquid in the cycle. Then what we call pump off. There is a part of the pump is not completely filled with it. What is with the pump intake pressure? What's the pressure with the pump intake pressure? How the downhole cart can inform me about pump intake pressure and the pressure? Downhole cart is a load, right? It's a load versus position, but there is no pressure measurement here. But remember, what is a load and what is the pressure? Pressure is a load, it's pound per square inches. And the load over the pump, which is lifted the fluid only. And the cross-section area of the plunger, all the load lifted in the cross-section area on the plunger. Then the fluid loads, the maximum fluid load in the pump, if I divided this fluid load to the cross-section area of the pump, this gives me the pump intake pressure. The pressure which is lifting from the step. What is a fillage? What's a pump fillage, as I say, and what's the pump displacement, how much the pump is produced, and so on. What's the current pumping speeds, just can measure from the surface, even it's not important to be downhole. The traveling standing valve condition is working okay, leaking, stuck, close, or close, open, and so on. What's the maximum, minimum pump loads, and so on. All this can be analyzing while I testing this the pump. And also, again, I repeat it, for the surface pump cart, you can analyzing, like a loading on the pumping units. You can analyzing loading in the rod string near to the surface. You can calculate the torque in the pumping unit. You can calculate the torque in the gear reducer. It wasn't allowed. It wasn't not allowed. You can calculate and analyzing the balancing the pumping unit. If the pumping unit is correct balance or under balance, over balance, and so on. And downhole cart also can detect a lot of problems. Not only give me some general information. No, it detect exactly some very very sensitive problem can be happen downhole. Like, remember when I tell you for deep wells I need to run with the tubing anchor catchers. Sometimes the tubing anchor catcher can come loose in the well, but from the surface you cannot know. You cannot see your tubing anchor catcher sitting at 6,000 feet or 10,000 feet down. But how I know that my tubing anchor catcher is still in position? I know. From your downhole carts, you can know. How? I will show you later on how we can do that. Traveling valve problem, close, stuck, leak, fluid pump have some fluid problems, pump leak, what we call over travel, under travel. Plungers move higher than its normal position or lower than its normal position. If there is friction, there is a leak, there is a gas, there is some tagging. Tagging means that while you are running the pump, it's a downstroke, the pump should be not completely, what we call not completely closed. The top of the pump should have at least, it's usually designed to have about half an inches or 1 inch is just the distance between traveling or standing valve, or just in the top of the pump, the valve rod. And so this special design, special calculations, maybe later on we can go if the pump is running okay or not, or just if hitting downhole or not. Again, let me just talk you about some generals downhole cards, shape of downhole card. When you can say, yes, this downhole card is good. No, these downhole cards indicate traveling valve leak. This downhole card is indicate standing valve leak. How you can analyzing this? How you do that? Remember, I inform you, if the pump completely running in a very good conditions, while the pump capacity either higher or equals the formation capacity, formation productivity, and the pump, there is all the valve running in a very good condition. There is no gas, and also the tubing anchor sit in place. It's not moving. The pump is running in very good condition, ideal condition. When you see the pump, this card, this dynamometer card, rectangular like this, you have two options here. First of all, my pump is running okay. This first impression, before, because I will show you on one other slide, sometimes the card will be completely full like this, but there is a problem. But when I see the pump cards completely rectangular like this, I need also to calculate my flow loads. Is this flow load from this point to this point, it's equal my actual flow load in the well, or less or high? Can be less, can be high. Why? I will inform you this later on. Let me just run some animation. What is mean of pump full completely ideal cards, and how this dynamometer card is going on and so. Remember, this pump, this is standing valve, this traveling valve, these plungers, while we are going up in the upstroke like this, traveling valve closed, standing valve is open, flow come from formation enter to the pump, while going down, traveling valve is open, all this flow displaces in the top, going up, traveling valve displaces all this flow to the tube. If you look here, at this point, remember, see here, at this point, here, these two valves closed while the pump is closed. While this just as soon, within less than a second, this start to hold all the load, and as soon as start to move, this load start to be increased, and when it reach to the full load lifted by the traveling valve, then the pump can be lifted the fluid, and traveling valve start to displace fluid. Since the traveling valve displace fluid inside the tubing, then this line will be like this, straight line like this. When we see this card in this shape, say that's pump full card. My downhole dynamometer card is a pump ideal. This can be give you some other indication. What's mean my pump card is ideal? That I have enough fluid to fill the pump. But sometimes maybe I have overflow more than my pumping capacity. That's still a room I can increase my production, because this means, yes, the fluid over the pump. The pump completely full with the fluid and the fluid. But where is I need to measure, in this case, the fluid level. I need to measure pump intake pressure. That's mean this ideal dynamometer card either to leave like it is, or there is, can tell you while you are analyzing, yes, still I have enough fluid, more room to produce the well. Then I need to run my well test, or just to, if I have a current in flow performance, to see, yes, this well now is producing, for example, 200 barrel per day. According to my well in flow performance, I still have a rooms to produce 300 barrel per day, and still have a pressure enough to fill the pump and have this condition. Try as much as possible to have this pump, your pump running in this condition, if possible, if you are able to get some more production. This is the ideals. Running life of your equipment will be good and so on. Okay? What if I have the fluid is not enough just to fill my pump? What's mean fluid not enough to fill the pump? That's mean by pumping capability, pumping capacity, and as a size and as a running parameters is higher than formation capabilities. Then The system is designed, or the pump designed according to stroke length, stroke per minute, pumping size to produce 500 barrel per day. But according to well productivity, the fluids, the formation is not able to give me 500 barrel per day. Give me only about 300 barrel per day. Then once the traveling valve is closed and going up, standing valve is open. While traveling valve is going up, fluid is going from down of the standing valve and fill the pump barrels. But traveling valve is going up at a certain point, traveling valve going up, and no enough fluid going, because the fluid at these pressures, hydrostatic head above this one, it's just able to reach to what we call static point. No more pressures can be able to push, no more pressure before below the pump to push more fluid inside. This is the maximum head I can have on that. In the pressure, if you measure pump intake pressure, you found from this point to this point only few psi. What we call pump fluid pounding is pounding fluid. This case, if there is no gas or just very, very few amount of gas, only liquids in this case, what happened in the downstroke? This in the upstroke, you will find almost a certain percentage of the barrel either can be in the up to these depths or up to this depths or up to these depths, up to this depths, depend on the amount of fluid. Then while we are going down for this stand traveling valve, in order to open, you must be compressed the fluid below the traveling valve. But since there is no fluid, then traveling valve will not compress anything here. Then traveling valve will be still closed. Then traveling valve will be closed. Since he moved in this area while there are no fluid, will be closed until he hit the surface of the fluid here. Then and when we hit the surface of the fluid, traveling valve start to be compressed this and open. But traveling valve, while we're going down with a certain speed, especially for downhole pumps, the highest speed at the middle of the pump. Then this, while we're going down and going with a certain speed, suddenly he found something just restricted the movement of the valve. Restricting the movement of the valve, it's a fluid, especially if this fluid have, very low API gravity, high viscosity. Viscosity is very high, the gravity is very low. Then it's working like, it's like some chalk downhole, it's just, hitting, the plungers is hitting the face of the fluid. All this hitting and just back a choke will back to the traveling valve, back to the rod string, back to the pumping unit, and can be easy damage of the pumping unit. How it looks like it was running. This is just animation to tell you how it's look like this and that. Because we said the traveling valve, while we start an upstroke in this point, two valves close and start to go up. The traveling valve hold all the load. While the traveling valve is going up, it just displace all the load up the tube. Traveling valve is closed here. When starting traveling valve going down, then starting valve is not, we found nothing of the fluid. Suddenly he found weight. This is just, due to some bouncy and you change the weight for that reason, you found this is small reduction in the load and going against gravity and so on. Then suddenly here he found hitting the face of the fluid. Then he lost the weight of the fluid, and at this point, traveling valve start to be open and start to be displaced the fluid. How it looks like in the animation. See here, the pump here is gap, no fluid. Then it's still close. Suddenly here, when you hit the weight of the fluid, it's open. It's hit the weight of the fluid in this point. Just try to see in this point with the other points in this point here. Here, it's hitting the weight of the fluid. Hitting the weight of the fluid here, because see, here just upstroke, start to go downstroke, standing valve, close, traveling valve, and now it's open. This is one of the worst condition you're running your pumping system as a road lift system. If anyone running road lift system with pounding condition, especially if it's at near just the middle of the pump, especially if you have no gas at all, especially if you have a high viscous fluid, very low API crude oil, like 20 API, 10 API, 15 API. This is one of the worst condition, and you will face a lot of failures for your surface equipment, downhole equipment. I'll show you in the failure analysis how this can be affected. What else I can find it in that gas? How the gas is affecting downhole pumps and downhole carts, and how it looks like, and how from downhole carts I can say, yes, there is a gas. No, there is a fluid pounding. No, there is some gas. How the gas affect, and how the pump running on the gas, and so on. This is a pump, and assumed that you have pump intake pressure is 200 psi. And the discharge pressure 2,500 psi. Okay, when you start to go up, all this hydrostatic head 2,500 psi effect on the pole of the traveling valve. Traveling valve is closed in this point. Meanwhile, still, because still I still inside, this is just closed, still inside the pump, I have 2,500 psi in standing valve closed. As soon as traveling valve is going out, what's going on? For no gas and no pump, you found this line was a straight line. But why here is have some curvature like this? When you start to go up, in order for this valve to be closed, the pressure here should be less than 200. But at a certain point here, this is going up. Since I have a gas, the gas have some expansion and still have high pressures. The pressure not yet released. And until the pressure at certain point, like point B here, once the pressure reach to a point less than 200, then in this point, standing valve start to be open. And traveling valve is moving here. Traveling valve is move and move float from here. The traveling valve is moving with this discharge pressure. Standing valve is open, and the pressure inside the pump is 190. But 190 is a fluid here is not only liquids, it's liquid with gas. It's just two-phase fluid. If you look here, it's two-phase fluid, liquid with gas. Then traveling valve, when it start to go down, what will happen? In order this valve, just here at this point, in order this valve to be open, then the pressure here should be higher than the pressure here. But below the pump and the valves here, what happened? This is a fluid with a gas. The valve here would change direction of the fluid. And this came closed cylinders, closed loop. Then traveling valve start to compress with a plunger, compress the fluid here, but compress the fluid step, just gradually, because more is moving gradually, Then start to compress the fluid. When compress the fluid, the pressure below the traveling valve was increased. Then the pressure below the traveling valve was increased. Then it's lifting a part of the load over the traveling valve. Then the load start to decrease gradually because the pressure here is increased gradually until we reach to point F. This point F here, where the pressure here will be higher than the hydrostatic head above the pump here, 2,510. It's not important to be 1000, but so this is just for an example to illustrate it for you how it's running. In this point, the standing valve, traveling valve is open and start to transfer all this flow to the pump. Then in case of gas interference, you found two curves. One small curve here depends also about the volume of the gas. Another curve here also depends on the volume of the gas, and because the gas is work like a shock absorber. This is case is problem, but not worst like the fluid pounding case. How's running just in animation? See this animation, is the gas going up, here start to compress until the compressed pressure here will be higher is open, here start to be closed until this pressure will be less than the hydrostatic head, and so on. Then you have a curve here and curve here. When you have these two together, that's mean you have gas interference, what we call pump is running with the gas interference. In the worst case, there is some condition. Can this pump reach what we call gas lock? There is difference between gas interference and gas lock. When the valve is open up at a certain position and the other is closed, open and closed, and there is a displacement, there is a production, what we call gas interference. What happens if I have a very high volume of gas here and I design my pump or I operated my pump? I will show you later on some pump design and operation problems can create it more problem in case of gas, what we call gas lock. Gas lock, that's mean when I reach to the bottom of my stroke and compressed all the fluids on the pump here, the pressure below the traveling valve is not higher enough. It's not reached to this point and in order to able to open this traveling valve. And in the upstroke, I open this up to the end, while the pressure here also is not decreased to up to enough value to allow the traveling standing valve to open. Then the pump is going up and down with two valves closed. Since two valves closed and gas inside the pump expanded and compressed with no enough pressure either to open traveling valve or to open standing valve. This is called gas lock pump. In this case, is also very bad condition. You will find no fluid at the surface. Okay. What about valves? If I have problem with the valve and some valve leaks and so on, look to these valves. You have some bitting, some problem, and so on. You know, while I'm going up, this valve should be hold fluid, should be hold the load. But since you have some leaks, in a part of this leak, fluid, since you have some problem, a part of this fluid will be leaking down, leaking again. Yes, it's hold a part of the fluid and moving up, you know, because hold a part of the fluid moving up. You'll find the curve. Since it's going up, a part of this fluid is just, you know, is leaking. Since leaking is lost a part of the weight of this one, lost a part of the weight in this one, especially also while in order going down, a part of this fluid is leaking is not enough to close the valve. When you found the top part of the valve in this curve shape, the upper part of the downhole card, it's represent the troubling valve operation. Lower part of the downhole card represent the standing valve operation. Try just to remember this. Then if I have the upper part like this, that's mean traveling valve because it's high load. And who's lifting the high load here is a traveling valve. That the traveling valve here is leaking. Then when you have this shape, that's mean traveling valve, it's leaking. How it looks like this, see here valve, a part of the float here, maybe it's not clear enough, but you know, if try to just look a little bit, part of this float, see, a part of this float is just leaking back. When you found it's not important to be in this shape, you know, depend in the severity of the leak of the traveling valve. But at least when you have something like this, that's mean traveling valve, it's leak and so on. Vice versa for standing valve. It's the same. If you found standing valve have some problem leak, you found the lower part of the dynamometer cards have this shape and this curve. And this is also animation of that. You know, while we are going down, this should be hold all the loads, all the flow. But while going down, part of this load is just leaking here. Then the load, it's not decreased suddenly. Load start to decrease like this and so on. This is what we call standing valve. When you found lower part in this curve like this, that's mean you have leaking standing valve. Okay? Sometimes I have all the valves running okay, I have enough fluids with the pump, but the problem will be with my pump barrels, the outer diameters. Because remember, we said for downhole pumps, I have 5 basic parts. The pump barrels, these are pump barrels, outer cylinders, traveling valve, plunger, traveling valve, standing valve, and hold down assembly. One of the main important pump is the pump barrels, which hold all the fluid inside this. The pump barrels, sometimes these pump barrels can have a problem, vent like this. And vent usually can be resulting from some collapse, some operation while I am running my pump in the well at the rig operation. If there is high pressure outside the barrel and inside the barrels, then maybe the barrel can be collapsed a little bit and so. The outer diameter of the pump the inner diameter of the pump at a certain point start to be low, very low like this. You know. If this is venting, it will be a very high, will prevent the plunger to move. But if it will be a very small pin, the plunger can be moved, but with a friction at this point. What will happen with the friction at this point? When the plunger starts to go up, if it's moving away from this point, it will work normal. But when the plunger start to hit this pinching point, what's going? Plunger going up, lifting the weight of the fluid. But here, when it start to go up, it's creating more resistance to pass from here. More resistance like an apparent fluid, like have an apparent loads over the pump. Then the load at that point will be increased while by going up. What happened while I am going down? When I start to going down, plunger, when we reach this, plunger should be going down, it's open, then the fluid load start to be go down. And I simulated this in the plunger when start to go down like here. Then a part of this fluid here in this area will be have like apparent fluid resistance, like a leak. Like a fluid is your missed fluid in this area. Then the bend will be downhole. Then in upstroke you have higher, downstroke you have low loads at a certain position. That means the barrel have some problem. Either could be scale sometimes, small scale, hard scale. It's not easy, but sometimes. In this case, you can say I have bent or sticking pump plunger. Sticking plunger that scale some problem. This can be here, it can be here, can be here, can be here. But usually in the same position, in the same area. If you are simulated this with this, you can found in the same area, like here, and this one. This is called what we call it's pump or just sticking or bending pump barrel. See in this point, in this area, here, in this point, try just to imagine plunger start to move here and just have some create more problem. Then when you have these two hints, just only one, one here and one here, like this, that you have some problem in the pump barrel. And this is exactly not 100%, but almost exactly in the same position like this one. Okay? What if I have vice versa? Plunger weird. That's mean, it's the side diameter in this area, it's increased. When the plunger start to move here, the plunger lost. It's not, you lose a lot of weight. All the weight is here. When the plunger in the upstroke going up, a part of this fluid circulated back. When it circulated back, like he lost a part of his weight. Lost a part of this weight, that's mean this have some problem here. But in this case, you not found here some problem in the downstroke, because in the downstroke, all the fluid, it's in the road, in the weight of on the standing valve. It will be applied in the standing valve in the tubing itself. And this animation of this one. I just try to show you some downhole cartridge animation, just to understand the basic of that, because usually in the oil and gas industry, you can find this, but you can find a combination of the problem, and this will be the problem if you can find some combination. What happened if my downhole tubing anchor is not holding in place? I run tubing anchor and assume that tubing anchor it's hold the pump, holds the tubing with the casing, which is preventing the tubing to move during the pumping cycles. In the upstroke, all the fluid load will be in the road of the road string. Then will be no load in the tubing. The tubing will be contracted like this and moved up. There will be no load in the tube. In the downstroke, all the fluid load will be back to the standing valve, which is a part of the tubing. Then the fluid load will be in the tubing. Then the tubing will be expanded, contracting and stretched, contract and stretch, going up and down. That's mean tubing anchor. There is no tubing anchor, or tubing anchor is not working. But since I'm going up here, here just when I start going up and this closed, all the weight is assumed to be on the traveling valve. And this line should be vertical exactly. But since the tubing is not holding and start to move up, then the tubing is also lifting a part of the fluid with you, like apparent fluid is lifted with the tubing itself. Then the line, while traveling valve is moved, and the road string move up, the line instead to be moving up like this. No, it is moving in this direction also, and because the tubing is holding a part of the tubing in the same of the down stroke and so. How it looks like in animation. See, this is a tubing. In the end, you see in downstroke, tubing is moved. In the upstroke, tubing will back in the same position as in this point. See, going up, lifting the weight of the fluid by traveling valve. On the rod string is lift all the weight of the fluid. In the downstroke, all the weight fluid going to the tubing, because there's no anchor, standing valve, tubing start to move and lines start to act. Then if you have a line, if you have a shape like this case, that's mean tubing and anchor. Sometimes a tubing is anchored, but it's not exactly 100% anchored. It's anchored, but if I released a certain weight over the tubing anchor, the anchor start to move within a certain inches, 1 inch, 2 inches small, just few inches just could be above or below. And this is one of the very worst condition if you have anchor and the anchor move, because the slips of the anchors, it will be eroded. It will be eroded the casing in this place, and it can be damaged casing in this place. How this looks like? It can be looks like this one. You will find tubing is still to hold, but when the load is decreased little more enough, then the tubing, the anchor is not able to hold the load and start to move. And the same here, in the same case. If you found some like this can be high, can be low, and this can be, depend on the movement and how far is moved, and so on. This can be have different, angles and so on. How it looks like can be looks like this, can be looks like this. Depend, wheel condition, type of anchors, tubing conditions, casing conditions, and so on. However, at the end, just you can find different combination. It's not an easy, you found one of these cases. You can find, for example, fluid bounding with gas interference. You can find fluid bounding with for example, with tubing and anchored. You can find gas interference with barrel bend. You can find a lot of combinations. Fluid bounding with standing valve leak, gas interference with standing valve leak. You can find 3 of that combination even together. Then depends in your experience, how you look like, take times in order to analyzing the downhole. What we are so now just in the screen, it's a real dynamometer cards. One card from one well, what is measured surface card, and based on that, calculated the downhole card. Based on this downhole card, if someone look to this, he say, yes, the pump is work almost ideal. You have a very good shape of the cards. That's mean I produce a completely fluid what the formation can give to me. Yes, you are right. But I inform you, when you are analyzing the cards, not look to one point, not look only to the shape of the card. Try to look also to calculation, to the value. I inform you before that for downhole cards, what's happened. For downhole cards, the loads here, it's a fluid load. And the fluid load is a function of this discharge pressure. This discharge pressure is a function of the hydrostatic head from the pump up to the surface, plus the wellhead pressure, plus the pressure. Plus. Then a certain value of the fluid here, I should be expected based also on the pump size. The peak polished rod load here, for this surface card, if you start to measure this surface card, remember in the design materials, there is 2 peak loads in the pumping unit, one in the upstroke, one in the downstroke. The peak polished rod, it's called, the weight of the fluid, the weight of the rod, the frictions, fluid loss, and so on. If I found the peak polished rod is less than the normal, because this should be a summation, fluid loads, friction loss loads, and the weight of the string. If I start to calculate this and found this is less, that means one of my parameters is not correct. The rod, it's not easy. I lost my rod? If I lost my rod, I cannot find downhole card like this. I found downhole card like a straight line. But I have a downhole card. Then I still have my bump with me. The bump's downhole. Then the road string is okay. No. Then I have a problem here. Load is less. I have a problem here. Load is less. What that means? That means the tubing could be leak at a certain depth. That's mean, but this leak over the fluid level, you know. That's means the pump, it circulated, lifting the fluid. For example, if I have my well produced from 6,000 feet, my pump sitting at 6,000 feet, I have a fluid level, I have a tubing leak at 4,000 feet. That means this fluid is equivalent to 4,000 feet, because at 4,000 feet, when the fluid reaches to the leaking point, it starts to circulate and go back, start to circulate and so. Then here in this well, if I measured the fluid load, I found less than my actual expected, predicted fluid load. There is this mean tubing leak. Also some other indication. I found my pump is producing like this. I have a tubing leak, and maybe I found my production at the surface, it's lower than normal, or no production. Sometimes I found no production if the tubing leak is big. Tubing leak is big, that's mean, you know, you have a tubing leak and all you are circulating. But if you have a small tubing leak, then yes, my production will be less, and could be this valve, this load will be a little bit different, can be higher loads up to a certain limit, because the friction loss will be less, and this requires a certain experience to indicate. But in these wells, there is no fluid reached to the surface. This is another also actual downhole cart. If you see downhole cart like this, someone will say, okay, this is for sure not downhole. This is not either surface or downhole cart. There is a certain problem. No, this is a cart, actual cart for surface and downhole. This is a surface cart, this downhole cart. It's from one well. When we found this one and start to just analyzing, we found the pump is stuck, and the rod have enough elasticity to stretch, because the stroke length, it's not big stroke length, it's more short stroke length. Then the pump start to go on, stretches the rod up to a certain point, which is not reached to the rod broken point, and then start to go down. This usually for short stroke length, high elasticity rods, and so on. You can find some like this. However, you know, I show you all this is actual dynamometer cart. In order to understand, you need to know the basic. If you know the basic, you can understand, you can analyzing your actual dynamometer cart. But keep in mind, dynamometer cart, it's not very easy to do. It's not just, you know, in some cases, you know, you need just to analyze more points inside the well. However, you know, there is some reference card. Maybe someone will say, okay, I don't have enough experience and so. However, the manufacturing, the engineering, and so is introduced to you some reference curves. You say you have some over 22 reference curves or more like this. If you found your dynamometer card, it's not exactly like this. It's almost in this shape, for example, or almost in this shape, for example, or almost in this shape, for example, you know. This indicate, for example, worn traveling valve, or just plungers, or just and so on. You know, it's not important traveling valve leak to be like a curve like this. It can be in this shape, is leaking and holding a little bit and leaking because the pressure start to be increased. You know, just the shape can indicate. Sometimes you have more friction downhole. Remember, I tell you that the load can be higher than normal, and this friction can be smooth friction, can be at the middles. Sometimes you are losing loads in the upstroke. This is a good part of the pump, top part of the pump have some problem. Then, you know, your downhole cart really, it's very good tools and important tools and essential tools. You will use it if you will work in any company running with road pumping system. You will use it. You will need for that. And maybe daily you will look to one of that cards and so on. There is a lot of reference cards which can help you if you are not have experience or just missed some of this interpretation of the cards and so on. Then one of the very important tools we said it is a dynamometer card. Dynamometer card, there is two dynamometer cards. One is the measured and one is calculated. The measured one is a surface dynamometer card. It is a relationship between the fluid load and the position, and it's measured at the top of the polished rod at the point while the polished rod it's connecting to the pumping unit at the carrier part, at the connection point, and it's used what you call load cell. I use this surface dynamometer card with information of my rod string, fluid loads, pump depths, my downhole pump size, my fluid properties, my pumping unit geometry, speed, stroke length, all that using some different equations. One of the main famous equation, well-known equation worldwide, it's wave equation introduced by Dr. Sam Gibbs. He predicted, simulated that you are moved your load cell to the top of the pump and then eliminated for you all the effect of the friction between rod and tubing, the weight of the rods, the geometry of the pumping units, and give you the net fluid load over the pump, while you can use just to analyzing your downhole pumps. Really, there is also a lot of research in this point. Some people use downhole card to just calculate the well production, how much downhole displacement. Some other people use to calculate the pump intake production, the pump intake pressure, and consequently the bottom hole flow pressure, and from production rate is used even to predict to construct the well inflow. Another tools is very important tools you will find in general for all artificial lift. Really, this tool is used for all artificial lift, not only for pumping unit, but also always is used for pumping unit. It can be used for road lift, for progressive cavity, for gas lift, for plunger lift, for electric submersible pump, and even some people try to use even sometimes in drilling condition to know where is the level of the mud in the well. What's called fluid level or acoustic well sounding techniques. Fluid level measurement using acoustic well sounding techniques. What does that mean? And what is acoustic well sounding techniques and so on. Acoustic well sounding techniques, that's mean I send some sound in the annular space between tubing and the casing, and I measured the reflect of the sounding, where the reflect of the sounding is measure each anomaly in the wells inside each change in the area between tubing and casing. It gives me some restriction. And what a change between tubing and casing in the area. Tubing connecting to each other with the collars. Then tubing, for example, if you have a tubing outside diameter 3.5 inches, the collar outside diameter will be 4.5 inches. Then at that 4.5 inches, the area between casing and the tubing will be less. Then the sounding techniques start to reflect, yes, there is an restrictions here. For each collar, it gives me a peak like this. For each collar, give a restriction peak like this. Until it's reached to the level of the float, it gives a big peak like this. That means here, there is no area. It's just plugged and so on. In this case, he says, this is the depth, this is the float level. How we measure the depth of the float level? There is different way, but the main way they measured, I know the tubing, what is running in the well. I know from my workover tally sheet what tubing I have, what the average tubing length I have. Then I count after I run, this is a microphone and this is a tools, like here microphone and tools connecting to the casing annulus. Then I count, here, how was the number of tubing joint from surface up to the peak of the fluid level. And for example, if this is 100 tubing joints and the average tubing length is 31 feet, then the depth to the fluid level, it's around 100 multiply 31, it's 3,100 feet. Then this fluid level is 3,100 feet. Some other people say, okay, maybe I'm not able to measure this peak. Then you measure the sound velocity. When the sound is going down like this, and maybe you can find fluid like that, not easy you found the weak. and it's hit the weight of the level of the fluid, sound is back to you again. If you measured the travel time of the sounds going up when it's going to hit the fluid and back again, and based on sound and sound velocities, then you know, yes, where is your fluid level and so on. Acoustic fluid level, it can inform you or can tell you what is the depth to the top of the fluid. It can inform you if there is existing fluid over the pump or not. If there is how much fluid in the casing. All the fluid in the casing is gas or just liquid or gas of liquid. If gas, how much gas? Because they are using a special technique in order to count this. You count fluid level in two times, in two different times. For example, now, then I close the casing for about 15 minutes, 20 minutes, I measure fluid level again. I measure the pressure build-up. There are special techniques in here. If you went to the website of Ecometer website, you can find a lot of information, animations, and the way it can inform you about how this is running, how it's working. Really, there is a very good information in even if you are doing some search over the website about acoustic fluid level measurements, you'll find a lot of information over it. However, you know, the benefits of dynamometer cards and the fluid level measurements, and so you need to detect your problem before it's too late. You need to analyze the continuous problem before it's too late, because too late that you create failure, you create problems, you are losing product, you are lost production. All that should be done by good monitoring, and I recommend a continuous monitoring like the well managers you have at the well site or connecting to your office and so on. Let me just, I give you some brief, you know, within the next 15 to 20 minutes about some problem and how can be solution. I'll try just, you know, in this lecture to highlight two main problems like a gas and sand, you know, and what we need to just to know how we can solve this problem and so on, you know. Reason of sucker rod problems, there is different reason for sucker rod problem, you know. What is that reason? One of them, it's back to you as a designer engineer or as an operation engineer or as a running engineer. You are not matched well production with system capability. Some people say, I need more production. Then you start to increase the pumping unit speed, stroke lengths, downhole pump size. He thought that with this one, he get more production. No, maybe he get low production. He running the system with high failures. Downtime must be very high. Then in order just, you know, to run your system in a good condition, you need to match well production with the system capabilities. Second, a proper system design. Based on that, you need to have a system design. Sand is one of the major problems for all artificial lift. Corrosions, you know, equipment quality. You have poor quality, especially for downhole equipment. You know, bad handling. Remember, artificial lift equipment is a very sensitive equipment, small equipment. Some people treat it and handling in a very bad way. I did some analysis with some of my friends, you know, for different fields. We found over 67% of the problem in some fields is related to handling equipment, how we handling the roads, how we handling the downhole pump. However, installation, monitoring, some people ignore monitoring and you not install gas interference, gas lock scale from water, from scale of gas, and so high water cut, some steam if you have steam injection, high temperature sometimes if you are not run the suitable pump, suitable metallurgy of the pump, and so on. For matching well condition with well production, usually, you know, it's typical problem. Either you can have fluid pounding. Remember the animation when I said you have fluid pounding, that's mean formation not producing enough fluid to fill the pump barrels, then the pump, part of the pump running under pounding condition, or you have a gas interference, you know, too much gas, or you have a gas lock. Usually, if you not match this exactly condition, you can have one or combinations of these problems and so on. What fluid pounding? Remember this animation? I inform you about fluid pounding. What fluid pounding can be resulting as a problem for my condition? Really, fluid pounding affecting all your system. From the surface equipment, remember, The pumping units is running with the gear reducers. And this is inside the gear reducer. The tooth is like this. If the tooth suddenly hitting each other and found sudden load, what happened for these tooth? The tooth can be broken in this case. The valve, traveling and standing valve, suddenly traveling valve or standing valve hit the weight of the float. Usually this is the seat of the ball. This is one. This is a part. This can be broken like this, can be broken in different case. Not only that, when you have some hitting the float inside this barrel, the barrel of the pump can be have some problem. Extension, the barrel can be splitted like this. Can have some, the extension of the barrel can broken. A lot of problem. This is just a few picture inform you for surface downhole, for the road start to be buckling, because you start to have some problem in bounding float start to be have some buckling. Remember also, it's bumping float or float bounding could be not only problem of there's not enough float. Maybe there is enough float, but you have bounding float. For that reason, I inform you, try to analyzing the fluid load and you run fluid level with your pump condition. Maybe you found bounding fluid and running fluid level, you found enough fluid of the pump. And fluid level load also, it's okay. Then that means formation have enough fluid and pump is not able to lift enough fluid. What that means? That means you have some restriction in the intake. Your pump intake here, it's plugged, have some problem inside the intake. This is prevent or restrict fluid, enough fluid to go, have high pressures here, or just restriction here in the standing valve and so on. Okay? Gas. What's a gas problem? Remember, gas is a big problem. Gas problem is the volumetric efficiency. Gas, since I will reduce my volumetric efficiency, I will reduce my total system efficiency. And it is similar like the fluid bounding, can create a lot of problem with the road, like a road buckling like this, can create problem with a pumping unit, but is less severe than pounding fluid and so on. But one of the major problems for the gas is the volumetric efficiency. Volumetric efficiency consequently is a total system efficiency. And gas, as I tell you, can create a very big problem for the road buckling like this. And if you have a road buckling, then have a tendency of the coupling of the road to contact the tubing and have some friction inside the tubing. The worst case of this one, as I said, I have a gas lock. Gas lock was when the gas start to increase, gas interference start to increase, and design the pump in a poor design is not a good design. What will happen here, Well, in this case, the gas can be expanded and compressed without opening the pump, and then you lose your production. You cannot produce and so on. This is just, a shape of what we call the gas lock. How is the gas lock in downhole carts? Downhole cart, remember, I tell you that the gas, you'll find this curve and this curve. But this curve for the gas and this curve should be going like this if there is a flow. But here there is no flow. It's completely curved like this. That means it is a gas interference or just gas lock. Gas lock start to be worst and increased until it reach to a gas interference and so on. How to calculate gas? There is different equation, but this is one of the main equations usually used to calculate the flow rate of gas. Because when we design your system, it's not an easy to eliminate the gas. Sometimes you are forced, you need to produce production. You need to run your pump intake pressures below the bubble point in order to get more production and so on. Then yes, it's okay to do that, but you need to calculate the volume of the gas. And in order to see, based on that volume, what type of pump I need, what type of configuration I need. Do I need a gas separators? No. Do I need a good venting efficiency at the surface? What will be my wellhead pressure? Because venting efficiency, that means the gas going to the casing and venting to the surface, against what pressures and so on. This is just, for your reference. These one equations can inform you about how much volume of gas. And as you see here, it's just, is a relation to the gas oil ratio at standard condition, and also just solution gas oil ratio and the pump intake pressures as a reference. Also, you need to know what's your production rates and bottom hole temperature, what your pump intake pressures, and so on. Sucrose pumping system for high gas ratio. In order just to produce oil, and you need to produce oil, and you found a lot of wells producing with a very high gas ratio and very high gas percentage as a pump intake pressure. In order to produce that, put in your mind, it's a very strong and very recommended. We are recommended to have what? First of all, try to have a very high percentage of the free gas prevent from entering the pump. If you can, it will be excellent to prevent the whole free gas as a pump. But try as much as you can to prevent the free gas to enter into the pump. If you are not able to prevent the whole gas or high percentage of the gas, you need to handle the gas. You need to work with the gas. Then the handle of the gas through the pump by applying a very good pump design. You need to run a suitable pump design, good pump design, which allow traveling valve and standing valve to be open as per its design and so on. One of the really very good techniques and very good approach usually used in the oil and gas industry for pumping road lift system with the gas is running downhole gas separators or running the pump intake below the perforation. If setting the pump or pump intake below the perforation, that's means this pump or the tubing intake below the perforation. What will be happen here, If I run my pump intake below the formation, the fluid usually is coming out of the formation. The gas usually have a tendency to going up, and the fluid have a tendency to going down against the gravity. In this case, you have a very good natural downhole gas separators, and you have a very good separation of gas. But meanwhile, you need to have a very good venting efficiency. The gas going out between the casing and tubing at the surface here, you need to vent this gas. Other than that, this downhole gas separator will not work. Meanwhile, if you are not able to run below the perforation, you can run downhole gas separators. In this case, there is different geometry of downhole gas separators and so on. Okay, then road pumping system for high gas oil ratio, it's recommended like this: setting the pump or intake below the perforation. Best location to set the pump or intake below perforation, either to have at least minimum feet below the perforation, is 20 to 6 joints of tubing below the perforation. This can allow to give you gas time to break, because when you have higher depths, you have higher time for the gas to go down and allow more gas to break. Because if I run the pump and take below perforation with 10 feet, 5 feet, 6 feet, then the gas maybe have not enough time to come out of solution and is moved to the fluid based on the fluid velocity and so on. Disadvantage of this one, you need to have what we call rat hole. Rat hole is a space of the well, is a part of the well drilled below the bottom of the perforation. This area, you need to have enough rat hole in order to run that. And also should be not have sand. If there is a sand usually is accumulated in this area and maybe plug the pump and take on. However, but this first option, and you need to look to your well configuration, your well design, how it looks like. And this at the end will be looks like this. Fluid come from the formation. Usually gas have a tendency going up, liquid have a tendency going down, and the liquids going up to the pump intake and going in this case. Then if it's not able to do that and to run below the perforation, my pump intake, then at least run the pump far, it's not against the perforation. Why I don't need to run my pump against perforation? Because this is a turbulent area. Gas come out of come with oil and very high velocity, come gas inside the oil, but I need to run the pump a little bit far away from that to give some times for the gas to come out of solution and venting. But meanwhile, I don't need to run this as shallow as shallower depths, because my pump intake pressure will be less. Same, and in that case, you need to run the gas separators. You run the pump 2 to 6 joints or 200 feet above the top of perforation, and in that case, you run downhole gas separators. There's different type of downhole gas separator in order to break the gas. Disadvantage here, perforation always have fluid above the formation up to a certain level, and maybe there is not enough just fluid velocity to separate the gas, and so on. How much, just the percentage of free gas, this equation can give you the amount of entering the pump based on the volume of the gas, based on the volumetric efficiency of the pump, based on the venting efficiency of the gas, and so on. How is the downhole gas separator? You need to put in mind how is it designed. It's designed usually based on the criteria. Free gas will naturally rise up, but in order to do that, you need to move the fluid. Gas separation occur when the fluid liquid move very slower than the gas rise. The gas usually rises at 6 inches per second. If you are stopped here, I've had the gas in normal cases, it's not in all cases, but in standard case, the gas is moved in approximately 6 inches per second. And in order to do that, you need to move the fluid with a speed less than this velocity of the gas. For the gas separation, for the gas separator, as a primary consideration for your gas separator, try to direct fluid downward to pump intake, just going downward to the pump intake for this one. Try to minimize fluid velocity as much as you can. Provide adequate storage for gas free inside the gas separators. Gas separators can be different type, as I mentioned before. It's not the time to go on each type, but at least to know there is some different type of gas separators. What type of pump? If I have a gas separator or not able to run gas separators, but if I have a gas separator but still gas going to the pump, is there is a pump inside the market can be handled the gas? Yes, there is a different configuration of the pump, or accessories can be run to handle some gas, or just to eliminate the gas problem for that. Remember, traveling valve, it will be open if the pressure above the traveling valve will be pressure below the traveling valve will be higher than standing valve. There is a certain technique, certain device called what we call top sliding valve. They installed this valve in the top of the pump. While in the down stroke, this valve is open and isolated all the weight of the fluid from the top of the traveling valve just and hold it by this valve. And it will be no fluid above the traveling valve. In that case, the traveling valve can be easy. There is another technique, yes, I need to consider one of the very important point while I design my pump, what we call compression ratio. The compression ratio, it is a total ratio of the total volume to the unswept volume between the traveling and standing valve. This is the total volume from here to here. When I open this up to the upstroke, what we call in this cylinder is the total volume. When I closed this one at the end, there is a volume here, what we call spacing in. Some people spacing the pump in a very worst condition. While we are closing the pump in downstroke, this is traveling valve stopped here. Then the area here, what we call the sweeping area. Then the sweeping area's total volume over non-sweeping, just non-sweep areas, the area is not already compressed. This is what we call its compression ratio. I need to minimize, compression ratio is an indication of the pump ability to compress the gas. When this is just, you have very low area here, then you have very high compressions capability of that fluid, And to minimize the compression ratio here in this case, I need to use, usually it's recommended, longer stroke lengths with a smaller pump. Because big pump, the area here will be big. Small pump, the area will be small. Longer stroke lengths will give me more space to go down. Then one of the very important considerations, when we design your downhole pump, you design the downhole pumps, it's recommended with a possible longer stroke length and smallest possible downhole pumps capable to achieve my target production. There is different downhole pump configurations can be used for this area. Try to reduce as you can the unswept area. This area, if you reduce as much as you can have a very good pump performance and efficiency in this case. Is there is another pump configuration can handle the gas? Yes, there is different pump. Remember, I need the pressure below the pump to be equalized. There is a pump in this shape, what we call variable slippage pump. This type of pump have two pumps inside each other. The first pump has bigger inside diameter. The lower pump has smaller inside diameter. When the traveling valve reached to the up and the end stroke, he also completed cycles based on design to go in this bigger poor size pump. Then the fluid start to slippage in the down, and they can have more fluid below the pump, then more fluid here. Then in this case will be more fluid, less gas, and this can be reduced the gas interference and so on. There's another different geometry, different type in the market, different configuration of the pump. There is another just brand new pump just introduced to the market, and it's planned to use in different area in Middle East called gas compressions pump. Use different technique from inside, different chambers and so on. However, I like just to let you keep in mind, you need to separate the gas. You need to run gas separators. Still in the market, there is a pump can be handle gas. This will allow you to use your sucker rod string in a very high gas or ratio wells. The technology is completely different than previous technology. What about sand? Sands can come from two different zones, two different areas come from. Either sand frac from the frac, after the frac, and this usually is temporary, because just maybe initial when we start to clean the well, clean the frac, and with the time it's clean itself. Or sand come from formation. Problem will be going, especially when maybe increased, and it's required special attention from your sites and so on. See this pump, have sand is completely plugged with the sand, Sand can create different problem, I need to understand the sand, what type of problem can be created, and the sand, how to avoid the sand, Sometimes you are forced to produce a sand. If I am forced to produce a sand, then what type of configuration I need to have down? Sand is a pressure material. It's very hard, one of the worst conditions. But sometimes I need to produce because I cannot make the formation produce the sand. Maybe I'm not able to produce to stop the sand. Especially it's a very fine sand, And sand when it start to enter to the pump can create pump sticking. Pump can be stuck inside the tubing, can create valve damage, can create plungers damage, can create a lot of damage for that. Pump valves weird, is a standing valve, traveling valve, and so on. See, this is a plunger, Plunger usually comes smooth in this area. But with the time, if there is a sand and you start to pull out of the well and start to analyzing, you found the plunger start to have a lot of scratch like this. Remember, scratch, that means it's reducing the plunger outside the emitter in this area. What that means? That a lot of losses, fluid loss can be slipped. What that means? That the mechanical efficiency of my fluids will be the mechanical efficiency of my pump will be reduced. Not only that, the fluid load. Imagine if you have a sand here and making all that soil, how much loads I need just to let the sand and the plunger move while they have this sand in this area. And not only that, it create a high pressure in the upstroke. In the downstroke, the sand stuck with just try to stack up, create high friction between plunger and the barrel. And this high friction creating a buckling for the road. Buckling of the road can create a very high road failures and coupling failures, tubing failures, and so on. However, for sand problem, it can be minimized by applying more than one solution. It can be one or more combined of one solution. First of all, try to prevent sand from entering the pump. Prevent sand from entering the pump, use sand screen, use some proper downhole, gravel back, whatever techniques. But sometimes, and in different times, is not an easy. But to prevent sand going to the pumps or just produce, I need to have a very good rat hole below the pump. And from time to time, I need to pull out my completion and clean all that rat holes. Try to put all this in mind, just, yes, there's a solution, but each solution requires a certain operation, certain cost, and so on. Use a proper plunger fit. Plunger fit, it means a clearance between plunger and barrel in order to allow for a certain size of particle can be passed without damage. Try to use a large valve bore. It's not always true in this condition, but it's required some expert how to design, what size of sand, what's the volume of sand, and what type of sand. Metallurgy, because the metallurgy is very effective with the friction, special type of pump, and so on. In all cases, if you have the sand and produce the sand, try to keep your pumping running continuous. Try to not stop the pumping. Sometimes the people stop the pumping for pumping of contention and so on. But in all cases, if you have the pump, it's strongly recommended to keep the pump continuous running operation, to keep the fluid, the sand moving with the fluid. For heavy crude oil and moderate crude oil, with a sand of between 5 to 10%, is depend on its viscosity. Sand usually tends to be carrying, suspended with the fluid, and so on. I'll try to stop here, because there is now almost 2 hours, and maybe, I don't like to be more heavy for you for this class and so on. Jumana, I will stop here, if there is more questions.
Thank you, Dr. Mohamed Ghareeb, for this enlightening session. Now we'll move on to answering some questions by our honorable audience. Someone says, could you please explain gas lock problem one more time?
Yes, gas lock, it's mean what we have. Gas lock, it's mean you have gas inside your pump. Gas inside your pump, that's mean my pump, in order to work and running smoothly, that's mean in the upstroke, my traveling valve should be closed, standing valve should be open, allow fluids to enter to the pump. New fluids coming from formation. The stroke, in the downstroke, my traveling valve should be open and displace this displace this fluid to inside the fluid. But if I have a gas lock, what will happen inside? Gas lock, that means gas lock the 2 valves close. It's not allow the 2 valves to open. Why? Because for traveling valve, in order to open, the pressure below the traveling valve in the downstroke should be higher than the pressure above the traveling valve. The pressure above the traveling valve is hydrostatic head. Below the traveling valve is a gas, and the gas is compressible fluids and will compress based on the area, the pressure inside, the volume, the volume where it's compressed, the temperature, and so on. If the volume is big and the volume of cylinder, is big, and the volume of gas is small, temperature is less, pressure is low, then the traveling valve will reach to the lowest point, while the sweep efficiency traveling valve is near to standing valve and is not able to create a higher pressure than the hydrostatic head. That means traveling valve will not be open. Going up in the upstroke, I have a pressure. I already compressed in downstroke. Going up, yes, I decrease this pressure, but the pressure is not decreased enough to allow standing valve to be open, because below standing valve is a low pressure, is a pump and take pressure, is a bottom hole flow pressure. Okay?
Someone says, what's the difference between gas lock and gas interference?
Gas lock, that means a pump is not produced. The 2 valves, it's closed in the up and down stroke. Gas interference, that's the pump is work, but the traveling valve and standing valve have some delay in opening. Traveling valve, it's open, but after a certain time while we're going down. Standing valve will be open, but while after a certain time of going up. While for gas interference, that's mean there is enough fluids with the gas inside the pump in order to allow the gas to be compressed. But for gas interference, it's been completely gas with a very few amount of fluid inside the barrel. The gas interference is the first stage before gas lock. You can have a gas interference, and if you are start to be worse and worse, gas volume increase, then you can have gas lock later on.
Someone asked, can two problems which affect the graph of the dynamometer?
Joanna, can you? I not hear you. Can you increase your voice?
Someone says can two problems which affect the graph of the dynamometer recording superimpose each other. Like for example, can the graph show a certain type of problem, but in reality there are 2 or 3 problems. However, the graph shows just one of the problems.
I not hear you because your voice is very low. What I understand that could be downhole card graphs show more than one problems, you know?
Can it have more than one problem yet show just one problem because they superimpose each other?
Yes, it can be have more than one problem, you know. For example, I can have float bounding with unanchored tubing. In this case, float bounding was an anchored tubing. You can find the shape of the float bounding, but tilted. The downhole cards will be tilted like this in this case. You know, I can have a float bounding, for example, with troubling valve leak. Troubling valve leak, yes, you can have bounding float, but troubling valve leak. Then you can have the shape is not exactly 100%. Can have a float bounding or just gas interference with what we call troubling valve leak. Yes, I can have gas interference with troubling valve leak. I can have 3 problems together, but in this case, you need just to understand your downhole condition. If you are not able to do that, you need a little bit experience. When the combination of problems can found, really sometimes it's required some more experience, some more analysis, take more time to analyze this.
Okay, someone asked if you could tell us about the mandatory info to analyze the rod system.
Joanna, I think you have some problem with your mic. I cannot hear you very well.
Can you hear me better now?
Yes.
Okay, someone asked if you could tell us about the mandatory info to analyze the rod system.
About what? Sorry?
The mandatory info to analyze.
About? The mandatory information about the analyzing system?
Yes.
Okay. Yes. One of the main important, I see majority of the people start to be ignorant, is the well inflow performance. You need to have in your hand the well inflow performance. Another information you need to have in hand your well completions. What is your well completion? Another things in hand, you need to have your current stroke length and your fluid properties. What type of fluid properties? Is my fluid properties change or just it's the same? Because you design your well to produce clean floats, only oils, and with time you found, for example, some problem, some bumps sticking, some bump like that, and the fluids, you know, just what we produce, sand start to come out of solution, and sand start to come with a fluid. Then sand, in this case, it's very important. You need to have your fluid properties. You need to have your current well testing. You need to have your well inflow performance. This is mandatory. You know, you have, and also if you're able, and it's very important to have fluid levels. If you have a fluid levels in front of you and the volume of gas, how much gas come out of solutions, how much gas around volume of gas venting from the casing. This is a very important information. If you look to one of the slides I mentioned, there is a lot of information you need to have, but as a mandatory information, like a well inflow performance, fluid properties, my downhole configurations, what a pump I have, what pump size I have, what the metallurgy of the pump size. Maybe I have a downhole pump size, it's just carbon steel, and I run this pump in a corrosive environment. I did my analysis, I say troubling valve, have some problem. But yes, I expected problem because water cut increased or just have some CO2, H2S while I am using metallurgy is not suitable downhole. What size of coupling? I am running in deviated walls, and I have a rod and tubing maybe is not designed in a very good ways. What type of sinker bar I used, and so on. Okay.
Okay, last question we have. How can someone prevent more gas entering through the pump?
How to consider more about the preventing gas entering to the pump?
Yes.
Yes. To prevent the gas entering to the pump, I tell you, one of the very good solution, cheapest solution, and very efficient solution to prevent the gas entering to the pump, to run the pump below the bottom of perforation, or at least the intake of the pump, the tubing end below the bottom of the perforation. In this case, the two phases of the fluid coming from formation, gas and fluid. Gas have a tendency to go up, fluid have a tendency to go down. In this case, it's one of the best performance technique to avoiding gas entering to the pump. But this one is required two things. First of all, you need to have enough rat hole, enough space of the from the well just below the bottom of the perforation in order to allow you to run the pump. Meanwhile, you are preventing the gas to enter to the pump. Where is the gas is going? It's going to the annulus between the casing and the tubing. Then the top of your annulus should have a very low pressure, either to connect to a special low pressure line or connecting to a low pressure wellhead line in order to allow the gas to go to the low pressures. Other than that, the gas will back again to the pump. The bad things of this one are just if you not have a rat hole or if you have a sand, the sand start to have a tendency to go down and will fill the rat hole in this one. But if I have these problems, then I need to run the pump in the top of the perforation. In the top perforation, but in this case, I need to run downhole gas separators. But the downhole gas separator for saccharode efficiency, it's not a very high because it depends on the gravity segregations of the gas. Then usually is run downhole gas separators with some equipment or tools with a pump to allow the pump to handle the gas and to design the pump with a very good sweep efficiency in this case and so on. Okay.
Okay, that's about it for the questions today. It was a pleasure having you today on PyroPetra, Dr. Mohamed Ghareeb. Thanks for joining us. I'm very glad I was able to attend again one of your lectures. This was definitely a very insightful session. Thank you everyone for tuning in with us today.
Shukran. Thanks for all of you.